Hello, and welcome to Maximizing Filter Performance. My name is Kirk Hetherington. I'm the Global Product Manager for Turbidity and Disinfection with the Hach company. Today, we'll be learning how to maximize your filter performance through knowing when to start and when to stop your backwash. Today, we'll be going straight through our presentation and saving our questions at the end. So if you have questions as we go through, please write them down so you have a chance to ask them at the end when we'll open up the line for questions. Well, with that, we'll go ahead and get started with our presentation. Maximizing filter performance is certainly a journey more than a destination. Even plants that are extremely well run may have symptoms that are coming out of some areas of their filter cycle and backwash cycle that are not yet optimized. On the left-hand side of the slide, you'll see a number of potential issues that may be present to one degree or another within your system. It's unlikely that any system is going to be affected by all of these issues, but it's likely that most systems are going to be affected by a few. So, for example, you may look at your process and think it's going really strong, but you may look at your turbidimeter readings on your filter effluent and wonder why they draw a straight line all day. It could be that that your process isn't really that variation. And if you think it's important to know what that variation is, this is some of the topics we'll be covering today. Likewise, are you convinced that your filters are running at the optimum length? How do you know? Are the inputs into your system always the same? And does your system always respond the same when you do consistent things with your process? If some of these questions resonate with you, it may mean that there's additional opportunity to maximize the performance of your filters. So that's what we'll be covering as we go through the presentation today. I'll give you just a moment to look through these questions and see if anything else resonates. Moving along, when we take a look at the filters themselves, why bother to maximize their performance? Well, these are hardly giant sandboxes when we talk about your mixed media filters. In fact, these are the most expensive and certainly most complex parts of most drinking water facilities. And this is because not only is it various layers of media, but these are dynamic processes that are constantly in flux. As such, this is the most complex process, likely to be the most complex process in your facility, and the use, even a good use of this resource, can incur significant cost, and the misuse of a filter or the suboptimal use can incur tremendous cost. Furthermore, by not optimizing your filter performance, you're likely to hide other issues that are present in other parts of your plant, whether that's your coagulation and flocculation, or perhaps even your pH. And of course, your filters are critical to the quality of your water. So to start, we're going to look at how a filtration process works in an ideal world. We need to acknowledge that this is an ideal world where cost is no object, and we know that in practice, very few plants work this way. But for the sake of setting what is ideal, we'll start there, and then we'll go into what we might see as a more practical way of working with filter optimization. So the best solution in this ideal world is gaining a stereo vision into your process. And what we mean by a stereo vision is by having two lenses so that you get the depth of what's happening in your process. This means using both a laser turbidimeter and a particle counter to characterize your filters through measurement. Now, it's no secret with Hach Company we'll be talking about measurement, but that measurement is going to be key as we go forward. Laser turbidity and particle counting measure different things. With laser turbidity, we can detect the presence of submicron-sized particles. And of course, as with all turbidity, laser turbidity determines the overall quality of water. Particle counting, however, is a little bit different. Particle counting detects the size and distribution of particles that are greater than 2 micron of size. This is the case in drinking water specific particle counters. In addition to that, that information gives gives particle counters the ability to identify pathogens and calculate their removal. So both technologies will help detect precursor particles to filter breakthrough. These are the particles that are very small and can be detected prior to a filter having an actual breakthrough event, and therefore they can tell an operator when to start a backwash. We'll spend some more time on this as we go forward. Additionally, because of the sensitivity, these instruments can help an operator troubleshoot their process and find the root cause of unexpected sources of variation within their process. And lastly, by having two instruments with an extremely fine level of sensitivity, we're able to confirm one event seen in an instrument with the other. Now, the optimization of filtration, as we discussed, will lead to uncovering and resolving other performance issues, such as coagulation, flocculation, and pH adjustment as well. So, why is so much measurement ideal? Well, there's a couple of reasons for this. Number one, the particles that are coming into a water plant are following a standard power law. So this means that the smaller the size of the particles, the more particles are present. And as an example of that, if in the sample we have a single 10 micron particle per milliliter, then that sample would then, in theory and in practice, contain 1,000 1 micron size particles and 1,000,000 particles that are 1/10 of a micron in size. So there's an awful lot of activity that's happening at that very low end of the measurement spectrum. Now, it's important, but what do we do with that? So what? Well, that activity is what we need to be able to detect in order to determine when to start a backwash. Traditional methods of determining when to start a backwash are based on time. How much time has the filter been in operation? Or head loss. What's the pressure gain of the buildup of water over the filter bed as the filter becomes clogged with more and more particles? So though those are in practice widely across the U.S. and around the globe, there are some shortcomings with that in terms of the potential costs that are associated with backwashing to time or to head loss. For number one, this could result in not using your filters to the full length of time necessary, which can result in extra electricity usage and also the water usage associated with the backwash, especially if it's going to waste, or having to reprocess more water by overwashing your filters. Additionally, the overwashing can lead to an extended downtime as the filter ripens to begin filtering out all the particles needed. And lastly, just because you may have a consistent time, especially if you're a surface water plant, it's unlikely that your inputs are always the same, therefore leading to process variation, which again can hide other issues throughout your process. If you look at this chart on the right-hand side of this particular slide, you'll see two data series. In the blue series on top, that's the data series for the FilterTrack 660 expressed in million TU. On the bottom, you'll see the data series for a Hach particle counter. Now, these are measuring a very low end of measurement prior to a filter backwash, which is the event you see on the right-hand side of the chart. What's important to note is that both of these technologies are showing a lot of variation at that low end of measurement and are detecting those fine particles as they come through the system. So as those particles are detected, you'll see an increase in the very small spikes, such as you see very clearly in the blue line of the FilterTrack 660 laser turbidimeter, which implies that a breakthrough will be coming soon. By using this information and studying the characterization of your filters, you're able to determine when to start a backwash, and that's the first half, and that's the first part of the equation for optimizing your backwash cycle. So that's how this process works in an ideal world, where you would have stereo vision from two technologies, laser turbidity through the FilterTrack 660 and particle counts through your Hach particle counter. However, we know that in practice, this is not often what happens because of the cost and complexity of this kind of measurement. We find that in practice, often most facilities can only fund half the implementation, which might be, for example, a particle counter and a conventional turbidimeter, such as the 1720 series turbidimeters. While the 1720 turbidimeter is a great instrument, it is certainly something that doesn't have the low-end sensitivity of a particle counter or the FilterTrack 660. So you only get a single vision to that low-end measurement. Additionally, that still incurs, by having two instruments, significant cost. Not only is there the instrumentation cost of almost $8,000 per filter to equip the filter with both an online turb and a particle counter, there's also nearly $1,000 a year per filter in calibration costs. We also know that in the realities of the constrained world that our facilities and our operators work in, their time is valuable and there's many things that they are asked to do. So keeping up with the increased maintenance needs of the particle counters is something that they have difficulty doing. And even if they're able to keep up with the cost and complexity of these instruments, we often find that there's just trouble interpreting the data for the particle counting itself, or even storing the massive volume of data that comes from the 8 channels of information from the instrument. And so because of that, many facilities end up coming to the conclusion that they simply do not have the time, the money, or the ability to provide the ongoing effort to reap the benefits of particle counting, and thus just use their regulatory turbs such as the 1720E to meet their basic compliance needs. Well, we'd like to submit that there's another option, rather than having a 2-instrument solution, to still get the benefits of optimization, and that's to use the FilterTrack 660. By using a laser turbidimeter, you get the ease of calibration that you do with a traditional online turb such as the 1720, and the familiar maintenance because the instrument comes in the same body style. Additionally, you get none of the application difficulties associated with particle counting, such as the clogging of the small measuring chamber, or measuring point rather, and the very high maintenance intervals. You get something that's much more user-friendly in the FilterTrack 660. And lastly, because the data is expressed in milli-NTU, it's a familiar parameter that's easy to interpret and certainly much easier to store. So if we have the use benefits of the FilterTrack 660, what else is different about the instrument? Well, the FilterTrack 660 has a sensitivity, as we discussed briefly earlier, that certainly rivals that of any particle counter in the drinking water industry. So particle counters in the drinking water industry typically measure particles that are greater than 2 microns in size, whereas the FilterTrack 660 can detect and trend submicron particles down to 1/100th of a micron in size. Now that's certainly a much more sensitive instrument. And when we look at this data series here on this slide, we can see that not only on the right-hand slide are both of these instruments picking up some of those minor breakthroughs in terms of the submicron particles that may be indicating a filter breakthrough, but there's even the event, and that you can see that in that central hump of the blue line of the data series on top of the FilterTrack 660, where there was an event that only the FilterTrack 660 was able to detect and was otherwise missed by the particle counter. And that comes from the increased sensitivity of the instrument. In addition to being more sensitive in terms of the size of particles that are trended by the FilterTrack 660 over particle counters, there's also the possibility that with this instrument, that is the FilterTrack 660, it can see events sooner than with a particle counter. In this data series, we can see, again, the blue line being a FilterTrack 660 and the purple line on the bottom being the particle counter. We can see the event in the middle that the FilterTrack detected 10 minutes prior to the particle counter picking up that event. So that's not always going to be the case, but certainly there's benefits to having a much more sensitive instrument. Thus far, we've been comparing 2 instruments that excel at the low end of the measurement spectrum. On this data series, we'll throw a third variable into the mix, which is that of the 1720 series turbidimeter, which is an extremely capable and sensitive instrument. However, it is simply in a different league than the FilterTrack 660 or a particle counter. When you look at that data series of the green line on top, that's the value coming out of the 1720E. And what you'll notice is that, for the most part, the instrument draws a straight line. However, if you look at the data series of the FilterTrack 660 and the and the particle counter, you'll see a lot of variation. We know that variation is happening, but the reason you're not seeing it in the 1720 series turbidimeter is that it's simply maxing out its level of sensitivity and is not able to detect those fine changes. That's why either a particle counter or a FilterTrack 660 is going to give that low-end sensitivity that you need in order to be able to detect those precursor events to particle breakthrough, or to filter rather. And lastly, we talked a little bit about the sensitivity of the instrument, but it's worth giving a concrete example of just how sensitive the instrument is. The FilterTrack 660 sensitivity is so fine that it's sometimes difficult to tease out from turbidity values alone what events are worth paying attention to. That's why we have a coparameter called relative standard deviation, percent relative standard deviation, or RSD, that we trend with this instrument. It's simply a mathematical calculation that compares current readings to the baseline readings of previous measurements. And what it is able to do is to amplify significant changes in the sample that would otherwise be missed by the naked eye. And so at extremely low levels, the RSD response can be 1 to 2 orders of magnitude greater than that of the turbidity measurement alone. And to give an example of this, we'll turn to the membrane filtration world. I realize that we're talking about optimizing traditional filters, but this example really gives a good indication of just how sensitive the instrument is. On a skid of 30 membrane tubes, with each tube having 1,000 individual membranes, so we have a total of 30,000 membranes being monitored by one FilterTrack 660. In this experiment, we essentially cut 6 tubes, and the instrument was able to give an over 1,000% response in terms of a change of its baseline. So the instrument went wild, and it was clear to see that the membranes had been compromised. We went forward repairing one membrane after another until all of them were fixed, except for one, which we had a single pinhole prick in one membrane of 30,000. The instrument still on the RSD had greater than 100% change from its baseline measurement, and thus was able to flag that there was still a compromise in the system. That's how sensitive this instrument is, to be able to determine one pinhole prick in 30,000 membranes. Truly a remarkable level of sensitivity. So if we're using that level of sensitivity to determine when to start a backwash, how do we know when to stop? Well, this is something that's done on a daily basis in plants around the world, and so there are many ways that have been able that we've come up with in terms of the operators to manage the process. There's time, which is a traditional measurement, terminating a backwash after a certain period of time, the volume of water or air that's pumped through the backwash cycle, even a visual judgment of clarity, which is always recommended, even with measurement, and lastly, measurement through turbidity. So there are certainly costs associated with underwashing or overwashing a filter. On the underwashing side, there can be the accumulation of solids within the bed, and this can create things such as mud balls or cementing portions of the bed, basically where some portions of the bed are essentially becoming offline because no water can pass through them, thus reducing the throughput capability of the filter and leading to shorter backwash cycles. And of course, with filters in general, when you don't have a filter that's performing, that can certainly affect the quality of your water. Now, overwashing can be no better than underwashing. The excess use of water is certainly a concern in some of the arid areas of the United States. Shorter filter runs or even the loss of filter media are some of the consequences that can come with overwashing as well. In addition, there's the increased operations cost in general, both in labor and in the resources to execute the backwash itself, and a ineffective filter ripening, as the filters must take in more particulate to begin effectively filtering the water that's flowing through. The American Water Works Association, or AWWA, recommends that a backwash cycle be terminated based on a measurement range between 10 and 15 NTU. That ensures that the bulk of the particulate is removed, but there's enough particulate left to ensure a proper ripening of the filter and a quick return to service. And so this is the guideline that we've always used going forward with our measurement of our backwash cycles and determining when to terminate them. If we look at this data series in front of us, we will see this from a drinking water facility. It looks like a pretty typical backwash cycle. In the backwash cycle, you can see that there is an extreme amount of overwashing going on. In fact, reading from the customer comment here, the thing that jumps out at you from these data is that the last third of the filter run, about 20,000 gallons, the backwash water is carrying very little solids off the filter, essentially wasted water. Given our 4,344 filter washes in 2008, this represents about 86 million gallons of water at a treatment and pumping cost of a bit over $21,000. So there's real dollars at stake and real consequences to a facility by overwashing a filter. And this is a good example of where a common paradigm or common way of thinking within our industry, better safe than sorry, sometimes gets us into trouble. Looking at a data set from a different facility, we can see that the same issue exists. If we were to execute the termination of a backwash at the recommended range of 10 to 15 NTU based on the AWWA guidelines, we would see that they are overwashing or they could reduce the backwash cycle of their filter by 2/3. If this is a facility that's struggling with capacity issues, this is a way to get significantly more water processed throughout their plant by simply optimizing their backwash time and minimizing the downtime of the filter. The solution for this, the instrument that we recommend for being able to measure when to terminate a backwash is the Solitax. The Solitax gives you the data you need, expressed either in NTU, and the range for turbidity in NTU is 0 to 4,000, or in suspended solids expressed in grams per liters. Either measurement will work just fine and is perfectly capable of being used in terms of maximizing your filter performance by the measurement cycle associated with the backwash. Additionally, whereas with the starting of a backwash, we're using the cleanest of waters and the finest of measurement, we're working in a very demanding setting here because of how dirty the water can be. And that's why that high range is important. And in addition, the feature of the Solitax, such as the wiper, which will help to keep the instrument in service despite any conditions your backwash might throw at it. The wiper can be adjusted with variable frequencies in order to make sure that your instrument is performing as needed. So with all things, having the right equipment is important, and the Solitax is certainly the right equipment. But location is also important, and in this case, location time is money. Analysis needs to be taken right at the point of the filter, and you really want to be as close as possible. If possible, we recommend mounting the Solitax in the backwash trough. It's important to note that by putting a Solitax in the wrong location, such as manifolding multiple filters to a single monitoring point or sampling a common drain, it is possible that you will not get the information you need in order to optimize your filter. So let's look at some of the locations where you might further optimize the filter itself. As we discussed, putting a Solitax in a backwash trough is what we recommend. You can see the red line there that represents the sensor, and just putting it in a single backwash trough is acceptable. Of course, in an ideal world, you would put one in each to get a total representation of the filter, and conveniently enough, our SC200 controller can accept inputs from 2 sensors. But again, we realize that most folks will end up using only one sensor in a fixed location. Because of this, though, and because of some of the large filters, the principle is still the same. You'll want to have one instrument fixed in the common drain gullet, and that's the blue bar there at the bottom center of the screen. And you'll also want to have another probe to be able to move around to ensure that the filter is being changed. Really, the principle doesn't change whether it's a small filter or a large one, but the ability to measure different sampling points across the filter becomes more important in a larger filter. We know that some operators will be tempted to use a single sensor across many filters, and as we mentioned just a few moments ago, it's important to realize that there are some limitations with this. By expanding the amount of time between the runoff from the filter, from the backwash effluent, and where it's hitting the sensor, then there's going to be a reduced amount of effectiveness of being able to optimize one's filter. Now, this may be a good place to start for people who are interested in testing out the ability to optimize their process, and certainly having one point of measurement is better than no measurement at all. But beware, if you use one sensor and a common point, you may have an unacceptable delay that will really inhibit your ability to optimize your process through measurement. So the question comes up, will you always save when you're optimizing your process? And particularly, we'll start with backwash. In terms of water, no. And this might be surprising, but as we discussed, underwashing is just as much of a problem as overwashing. And if a facility has been underwashing for some time, then it's going to take some time to unravel those problems through longer filter runs. Once that's done, and once those filter runs have been optimized, then water savings will start. In the end, however, our experience shows, working with a great number of facilities, that operation expense are always saved in the end. And that's through savings in power, the retreatment cost, labor, filter media, protecting that investment in your most important and complex process, which is your filters, and uncovering other areas of the process that are yet to be optimized, such as we've mentioned before. So in the end, we find that savings almost always follow. However, sometimes you've got to overcome some inefficiencies that have been built in the past. So in conclusion, backwashing to measurement certainly reduces the process variation, which allows you to have more control over your process. It protects your investment in your filters, reduces operating expenses in the long term, and also has long-term water savings. Measurement, such as with a particle counter or specifically the FilterTrack 660 laser turbidimeter, can help determine when to start a backwash, ensuring you're getting the most out of your filter run times. And by using a Solitax to monitor your backwash, you can know when to stop a filter and making sure you're getting the most out of your backwash cycles. So measuring when to start and when to stop are both critical in terms of maximizing your filter performance. We realize we've thrown a lot at you in the course of this presentation, and so we'd like to point out a number of resources that are available for you offline. If you go to the links that are provided below, then you will be able to find that information and read on these papers and have a little bit more time to digest it and go into a little bit greater analysis of these processes. So please consider joining us on the web at those sites to be able to get some information. And with that, we will go ahead and end the formal part of the presentation and open up the line to questions.